Just keep going. So Locke's language, I'll find his original repository, I guess. And see if he has the grammar written anywhere. Oh, grammar.dart. Oh, no, that's not it. All right, so you're talking about 3.7 here.
It calls it a statement. It says that the statement inside.
Right. So, okay, maybe what I'm missing is we haven't talked about statements at all. So maybe what we were modeling here is just the expression, like example that he had, like this.
Yeah, I think it's just parents, basic operations, constants, literals.
And not the entire grammar. So where's the entire grammar? Okay, blah, blah, blah. Yeah. There we go. Yeah, so if is a statement type. Yeah, gotcha. Okay, so here's the whole grammar. Once we get around to it.
Okay.
So I was thinking, do we so the most straightforward way to translate these things is he makes a Java class, so we can make a struct. I wonder why we tried to do enums here, actually.
Well, enums is a natural way to represent some kind of type structure.
Yeah. So the difference between doing it this way and doing it with structs is we don't have names for these. They're just the fields of the enum type.
We can have named enums. That
Really?
doesn't change. Yeah.
So
If you replace round parents with braces and not names.
I didn't know that. That's cool. Cool. So yeah, then we can generate the same names that he even has in his syntax. So what's he okay, it's in the chapter 5, and he has the syntax that he's parsing, and it's like type expands to this. And the expression has the following variants. So yeah, those are easy then. And then when we got down to literal object value, how did we know that these were the possible values of literal?
a logos language describes as booleans, numbers, strings.
Yeah. I guess the question is, how would a script know that? How are we specifying it to a script? So if he has
We might not even
Yeah.
need to have a script. Like one place he uses generated code is to AST printer. In our
mhm,
case, it's just derived debug. Next, he will need some parsing, but it's not that much more difficult to write it by hand.
okay. So you think we're not going to end up doing macros?
Well,
Won't need to.
let's still try to write it by hand.
Yeah.
If it becomes too clunky, we can always try make a
Yeah.
macro.
So you're right. Okay. I'll start writing it by hand. If we have an expression, and then we call this yeah. Go ahead and make the grouping. He calls this expert unary. He calls this is the named enum variance like a sort of a recent thing?
Now it's been since forever, I think. It's not any different from name struct.
Yeah. I guess this, yeah, generalization.
The binary one is also named operator.
Thanks. Okay.
And he's calling the grouping one expression spelled out.
Grouping needs to exist because at some point we have to deal with parentheses
Mhm.
and
Yeah.
decide what takes priority between like addition, multiplication.
Okay. And
But,
then
but doesn't the AST already represent that? The shape of the tree tells which operator to do first.
Maybe.
well, we need to store those nodes in order to figure out aren't we're building the AST right now. Oh, I see you asked this. So it depends what we do when we parse it, right? Are you saying just like get rid of the parens in the process of building the AST? Essentially.
No.
Basically, yeah. Like expression in a parentheses means the same thing as the expression itself.
Yeah, I don't
Yeah.
mind trying that.
I mean, it's not. I don't think it's. There's no harm in having it there either. You wanna
Yeah, I'm
be
just gonna
true,
I'm just gonna go through sort of the exercise for this small subset of the grammar, and we'll see what kind of things we run into. It's possible that, yeah, like this is only useful as we're building the tree, and then eventually we can get rid of it.
It might be useful for pretty printing.
Yeah, yeah. Pretty printing the code, you would still need to know. Um, okay. Are we still going to try to do string references? And so do have the whole lifetime thing?
Uh,
That would sort of infect everything,
hmm,
right? Yeah.
It will be difficult to make it boxed. Let's try to get rid of it for now. We can add it later.
Okay. So that means this has a,
Yeah, it's capital string.
okay.
Before
What
with an
are-
ampersand string.
Yeah, before it was a reference to a str.
Yeah.
Now it's an owned string, like a heap allocated, well, not necessarily heap allocated, but
Now it's a string, capitalized string is always heap.
it is.
Yep.
Binary operator. What are the possible binary operators?
Uh,
Yeah, are they down here?
yeah, we have them.
Are these? Bang is not one.
Then addition, multiplication.
Yeah.
Have them somewhere.
Maybe these are the names of the tokens, not the names of the nodes. So I think I'm just going to go back to the grammar, see what his binary operators. Oh, he has like literal values in here. That's interesting. We can't do that.
We can be like a constant, but it doesn't really make much sense. What he specifies is the grammar. It's not the actual code.
Yeah. So is this even a thing that can be turned into? Is he even passing the grammar into like his code generation, or is it merely like documenting the grammar, and he's just implementing it?
He probably generates something from that. So parsing expressions.
So he's generating.
Those are operators.
Yeah. Okay. Okay. I'm just going to guess, and then if we are missing any, we can add them. Okay. So we start with that. Bunch of enums. Then for each of these, we need this visitor.
What does it do? I did some Java magic.
Yeah, so this is the visitor pattern. It does the point of it is to have a separate, let's see, I have some like descriptions here. The point of it is when you want to define a new way of processing a node. Oh, thanks for these. When you want to add a new way of processing a node, you don't need to reach into the code for all the nodes. So the way it works is,
All right, I remember that.
So your operation calls visit a particular visit method on the node type, and then this figures out. Oh, it accepts. You write an accept method that takes any generic visitor. So accept is generic over the visitor type. And then the visitor, there's sort of one visitor interface per type of node.
That's horrifying.
That's the standard for Java. It's a design pattern. It's like a sneaky trick somebody thought of to do this weird thing. We did it in my compilers class. We made visitors. So what's the best way to do it?
I am not sure what kind of operations we'll need. But if LVK is like calculating the values and printing, we don't really need any fancy visitors, I think. And just calling the method and doing some pattern matching.
Yeah. So do they do this visitor thing because they can't do match statements and enum types?
So what would you be matching over? The type of visitor, or what?
The type of the expression, or like the enum variant of the expression.
So
well, we have a top level expression and type called expression. We add the method called eval.
So they're sort of thing. So the visitor type will have like one method, one visit per node type. So visit opinion. And so on. Each so the trait, I guess, the pastry trait has an accept, which takes some visitor, any visitor, except some visitor. And then, but all that does is call the appropriate method up in here. So, yeah. So where would you put the match, I guess? if you were doing this in Rust. So
Yep.
it's- so we still want this as a struct, I think, because we want to have one type that is like one way of processing the nodes. So whatever.
Well, if you want
Does it-
typical implementation of visitor trait in Rust, that's what Serde does. But that's exactly why Serde is miserable to use by hand, or if you're doing anything remotely interesting that you cannot describe with drive macro.
So it's not, it's a match over the type of the node. I don't know why I'm still saying pastry. So
Serde just adds a whole bunch of methods, visit for every specific node type. Yeah, that's authorship elimination.
yeah. Ample visitor. What is this? Just a lifetime? What is it?
It's
DE?
a lifetime deserializer.
Okay. Is it stir? Hmm.
Yeah, I agree with Ricardo. I think recursive pattern matching and just recursive methods is going to be easier to implement.
Okay. So, okay, let me see. Let me see what they're saying. So you have an expression. Match the expression based on what type of node. I guess so this is the implementation for one visitor type. Is that what you're saying? Because
No,
I don't know if the visitors all recurse down the tree in the same way. Like they probably do.
so what I'm saying here on chat is we don't do any visitors, like
Mhm.
because Rust already has this like enums that you can pattern match, right?
Yeah.
So you just do pattern matching recursively because like you have an expression enum that has like, for example, the binary operation has like two like children expressions. So you visit them recursively and so on and so forth. I know the book maybe tries to go in the visitor way, but I don't think that it's necessary.
Yeah.
Maybe it would be like necessary for like, I don't know if that's even relevant. Like if you end
Well,
up like, recursively doing way too much stuff until you Stack Overflow, but I don't think that's the case.
yeah, you probably recurse out to the. So what we're trying to do is build the tree, right? That's. So I want to see sort of what a few things that he does with the visitors, because he spent this chapter describing what a grammar is and then how to write the visitor pattern. Then what does he actually do? So In this one, I think he just pretty prints. So that, okay, right. So he did all the parsing by hand here. And so given an AST, you can pretty print it. I don't care about that. I want to know, do we need visitors to even make the tree? Or not?
In my experience, you don't need visitors like for anything really. I have like a couple projects regarding programming languages. 3 of them. One of them I just kind of finished last time, and at no point I really went for a visitor. Like the parsing is just going over tokens and like I did on my own thing there.
I'm skipping ahead. I'm gonna see what he does because I think you're right. So the parsing is just sort of a loop over tokens.
Kind of, yeah. Like you consume tokens, you go over like for instance, you expect this token to parse like a class, so the next one you expect a identifier, then some kind of like curly braces and so on and so forth. Parsing is, I think, the most boring part of for me at least, but it's we need to do that, of course.
Yeah. So, okay, I'll skip visitors. It sounds because like it's like we're setting up machinery that we will need to traverse over the tree later, but we don't need the same machinery in Rust.
No, Rust kind of already have.
Yeah.
Already,
because you have pattern matching. Yeah. Okay. This makes sense. Now, is the traversal? You think the traversal over the tree is the same for every visitor? Because like the example you posted is like are you recursively calling a val on the other expressions?
That's for like when we already parsed it. So this is already parsed. This is an example where everything is parsed, everything is beautiful. We just want to evaluate this.
Yeah.
We kind of do that for a tree, what's it called? Tree walker.
Yeah.
Probably the VM approach is faster. So for parsing, I guess we also don't need to worry too much about visitors. At no point I think we need to worry about visitors. Maybe he will use visitors, but we can probably emulate.
I would expect he uses visitors for evaluating. Yeah, there we go. But not parsing. All right, so how about this? Why don't we just start reading chapter 6 then? Because we don't we have like a theory of how to iterate over the tree, but it doesn't require visitors. So we might as well just read about how he's parsing.
Yeah. Do we have a Lexer already?
Yeah, we do.
Okay.
Yeah, there we got that. That was chapter 4, and it actually described like the whole thing, how to do it. So we have a few tests there.
Cool.
Yeah. Okay. I guess yeah. Well, we'll just come back to that. So I will just start reading chapter 6, and I don't know how it seems pretty long, so we'll probably not finish it. So yeah, we'll start reading. All right. So parsing expressions. This chapter marks the first major milestone of the book. Many of us have cobbled together a mishmash of regular expressions and substring operations to extract some sense out of a pile of text. The code was probably riddled with bugs and a beast to maintain. Writing a real parser, one with decent error handling, a coherent internal structure, and the ability to robustly chew through a sophisticated syntax, is considered a rare, impressive skill. In this chapter, you will attain it. It's easier than you think, partially because we front-loaded a lot of the hard work in the last chapter. You already know your way around a formal grammar, you're familiar with syntax trees, and we have some Java classes to represent them. The only remaining piece is parsing, transmogrifying a sequence of tokens into one of those syntax trees. Some CS textbooks make a big deal out of parsers. In the 60s, computer scientists, understandably tired of programming in an assembly language, started designing more sophisticated, human-friendly languages like Fortran and Algol. Alas, they weren't very machine-friendly for the primitive computers of the time. These pioneers designed languages that they honestly weren't even sure how to write compilers for, and then did groundbreaking work inventing parsing and compiling techniques that could handle these new big languages on those old tiny machines. Classic compiler books read like fawning hagiographies of these heroes and their tools. The cover of Compilers, Principles, Techniques, and Tools literally has a dragon labeled Complexity of Compiler Design being slain by a knight bearing a sword and shield, branded LALR parser generator, and syntax-directed translation. They laid it on thick. A little self-congratulation is well-deserved, but the truth is you don't need to know most of that stuff to bang out a high-quality parser for a modern machine. As always, I encourage you to broaden your education and take it in later, but this book omits the trophy case. Ambiguity and the parsing game. In the last chapter, I said you can play a context-free grammar like a game in order to generate strings. Parsers play that game in reverse. Given a string, a series of tokens, we map those tokens to terminals in the grammar to figure out which rules could have generated that string. The could have part is interesting. It's entirely possible to create a grammar that is ambiguous, where different choices of productions can lead to the same string. When you're using the grammar to generate strings, that doesn't matter much. Once you have the string, who cares how you got to it? When parsing, ambiguity means the parser may misunderstand the user's code. As we parse, we aren't just determining if the string is valid LOX code, we're also tracking which rules match which parts of it so that we know what part of the language each token belongs to. Here's the LOX expression grammar we put together in the last chapter. This is a valid string in that grammar, 6/3 - 1. But there are two ways we could have generated. One way is starting at expression, pick binary. For the left-hand expression, pick number and use 6. For the operator, pick slash. For the right-hand expression, pick binary again. In that nested binary expression, pick 3 - 1. Another is pick binary for the left-hand side. And then in the nested binary expression, pick 6/3. And then at the outer binary, pick minus. And then for the right-hand expression, pick 1. So the associativity or the precedence could have been different. These produce the same strings, but not the same syntax trees. In other words, the grammar allows seeing the expression as 6/3 - 1 or 6/3 - 1. The binary rule lets operands nest any which way you want. That in turn affects the result of evaluating the parsed tree. The way mathematicians have addressed this ambiguity since blackboards were first invented is by defining rules for precedence and associativity. Precedence determines which operator is evaluated first in an expression containing a mixture of different operators. Precedence rules tell us that we evaluate the slash before the minus in the above example. Operators with higher precedence are evaluated before operators with lower precedence. Equivalently, higher precedence operators are said to bind tighter. Associativity determines which operator is evaluated first in a series of the same operator. When an operator is left associative, think left to right, operators on the left evaluate before those on the right. Since minus is left associative, this expression 5 - 3 - 1 is equivalent to 5 - 3 minus 1. Assignment, on the other hand, is right associative. This A equals B equals C is equivalent to A equals B equals C. Without well-defined precedence and associativity, an expression that uses multiple operators is ambiguous. It can be parsed into different syntax trees, which could in turn evaluate to different results. We'll fix that in LOX by applying the same precedence rules as C, going from lowest to highest. Here's a table. Right now, the grammar stuffs all expression types into a single expression rule. That same rule is used as the non-terminal for operands, which lets the grammar accept any kind of expression as a sub-expression, regardless of whether the precedence rules allow it. We fix that by stratifying the grammar. We define a separate rule for each precedence level. So, right. Higher precedence things can only become lower precedence things, which he'll fill out, I guess. Each rule here only matches expressions at its precedence level or higher. Yeah. For example, unary matches a unary expression like bang negated, or a primary expression like 1, 2, 3, 4. And term can match 1 plus 2, but also 3 times 4 over 5. The final primary rule covers the highest precedence forms, literals, and parenthesized expressions. We just need to fill in the productions for each of those rules. We'll do the easy ones first. The top expression rule matches any expression at any precedence level. Since equality has the lowest precedence, if we match that, then it covers everything. Over at the other end of the precedence table, a primary expression contains all the literals and grouping expressions. So literals or parenthesized. A unary expression starts with a unary operator followed by the operand. Since unary operators can nest, bang, bang, true is a valid if weird expression. The operand, it can itself be a unary operator. A recursive rule handles that nicely. But this rule has a problem. It never terminates. Remember, each rule needs to match expressions at that precedence level or higher. So we also need to let this match a primary expression. So it can be bang or minus, and then a unary or primary expression. That works. The remaining rules are all binary operators. We'll start with the rule for multiplication and division. Here's a first try. So factor goes to a recursive factor expression, and then either slash or times, and then unary, or unary, just unary. The rule recurses to match the left operand. That enables the rule to match a series of multiplication and division expressions like 1 star 2 slash 3, putting the recursive operation or production on the left side and unary on the right makes the rule left associative and unambiguous. All of this is correct, but the fact that the first symbol in the body of the rule is the same as the head of the rule means this production is left recursive. Some parsing techniques, including the one we're going to use, have trouble with left recursion. Recursion elsewhere, like we have in unary and the indirect recursion for grouping in primary, are not a problem. There are many grammars you can define that match the same language. The choice for how to model a particular language is partially a matter of taste and partially a pragmatic one. This rule is correct, but not optimal for how we intend to parse it. Instead of a left recursive rule, we'll use a different one. This is interesting. So factor is no longer recursive, but it has any number of these groups of either slash or star and then a unary expression. At least one unary followed by any number of these additional groups. We define a factor expression as a flat sequence of multiplications and divisions. This matches the same syntax as the previous rule, but better mirrors the code we'll write to parse LOX. We use the same structure for all the other binary operator precedence levels, giving us this complete expression grammar. So everything goes to the stuff of higher precedence. So I'm interested in why. So the only reason that you're allowed to use a recursive rule for unary is because it's not binary. So you don't need to worry about the left recursive problem, but everything else needs to descend a level. This grammar is more complex than the one we had before, but in return, we have eliminated the previous one's ambiguity. It's just what we need to make a parser. All right, recursive descent parsing. There is a whole pack of parsing techniques whose names are mostly combinations of L and R, LLK, LR1, LALR, along with more exotic beasts like parser combinators, early parsers, the shunting yard algorithm, and pack rat parsing. Don't know about any of those, really. For our first interpreter, one technique is more than sufficient: recursive descent. Recursive descent is the simplest way to build a parser and doesn't require using complex parser generator tools like Yak, Bison, or Antler. All you need is straightforward handwritten code. Don't be fooled by its simplicity, though. Recursive descent parsers are fast, robust, and can support sophisticated error handling. In fact, GCC, V8, the JavaScript VM in Chrome, Roslyn, the C# compiler written in C#, and many other heavyweight production language implementations use recursive descent. It rocks. Recursive descent is considered a top-down parser because it starts from the top or outermost grammar rule, here expression, and works its way down into the nested sub-expressions before finally reaching the leaves of the syntax tree. This is in contrast with bottom-up parsers like LR that start with primary expressions and compose them into larger and larger chunks of syntax. A recursive descent parser is a literal translation of the grammar's rules straight into imperative code. Each rule becomes a function. The body of the rule translates to code roughly like, so for terminals, code to match and consume a token. Non-terminals, a call to that rule's function. A pipe. So a pipe
No,
within the
or.
grammar notation.
Right, an alternative in the grammar notation.
Yeah. I switched if one of several cases. This becomes iteration, and then this becomes just an optional. The descent is described as recursive because when a grammar rule refers to itself, directly or indirectly, that translates to a recursive function call. The parser class. Each grammar rule becomes a method inside this new class. All right. So we've got a parser. It's got, I think we might have already made this skeleton somewhere. You give it a list of tokens, and then it's going to keep some state to like figure out where it is in parsing. Like the scanner, the parser consumes a flat input sequence, only now we're reading tokens instead of characters. We store the list of tokens and use current to point to the next token eagerly waiting to be parsed. We're going to run straight through the expression grammar now and translate each rule to Java code. The first rule, expression, simply expands to the equality rule, so that's straightforward. Okay, so yeah, okay, it's pretty clear. Just return whatever equality is, just like the rule here. Each method for parsing a grammar rule produces a syntax tree for that rule and returns it to the caller. When the body of the rule contains a non-terminal, a reference to another rule, we call that other rule's method. The rule for equality is a little more complex. So equality goes to comparison, followed by any number of equals or not equals, and then another comparison. So you get one comparison expression, parse one comparison expression, and then, yeah, a while loop over
The next upcoming token.
Yeah. So I guess what's weird is there's some state being managed in the background for which token you're at. Because match, like this has to be, yeah, this is a helper function where he's advancing through tokens. Yeah, so yeah, again, we had to do this for the Lexer, so I don't think it'll be that tricky. You can probably use a similar pattern. So he's going to, while the next token is either bang equal or equal, operator equals that thing you just looked at, and then parse another comparison operator, and then return the result of, you know, the tree with left operator right. Oh, well, he's probably just going to say what I just said. Let's step through it. The first comparison non-terminal in the body translates to the first call to comparison in the method. We'll take that result and store it in a local variable. Then the star loop in the rule maps to a while loop. We need to know when to exit that loop. We can see that inside the rule, we must first find either a not equal or equal token. So if we don't see one of those, we must be done with the sequence of equality operators. We express that check using a handy match method. So what is this?
It checks against the entire list of things that were passed to it and matches on any one.
Matches on any of the types that you passed. Okay. But also advances, weirdly. This checks to see if the current token has any of the given types. If so, it consumes the token and returns true. Otherwise, it returns false and leaves the current token alone. The match method is defined in terms of two more fundamental operations. The check method returns true if the current token is of the given type. Unlike match, it never consumes the token, it only looks at it. So if you're at the end of the tokens, it's always false. Otherwise, you need to peek. So peek is just get the current token. And then check the type. Advance consumes the current token and returns it, similar to how our scanner's corresponding method crawled through characters. So advance this iterator position and return the token that you just looked at. I don't know why he's like, he's advancing first and then calling previous to get the one that you just passed over. Whatever. These methods bottom out on the last handful of primitive operations. Yep. Is at end checks if we run out of tokens to parse. Peek returns the current token we have yet to consume, and previous returns the most recently consumed token. The latter makes it easier to use match and then just access the just matched token. That's most of the parsing infrastructure we need. Where were we? Right, so if we are inside the while loop in equality, then we know we have found a not equal or equal operator, and we must be parsing an equality expression. We grab the matched operator token so we can track which kind of equality expression we have. Then we call comparison again to parse the right-hand operand. We combine the operator and its two operands into a new expr.binary syntax tree node, and then loop around. For each iteration, we store the resulting expression back in the same expr local variable. As we zip through a sequence of equality expressions, that creates a left associative nested tree of binary operator nodes. Yep. The parser falls out of the loop once it hits a token that's not an equality operator. Finally, it returns the expression. Note that if the parser never encounters an equality operator, then it never enters the loop. In that case, the equality method effectively calls and returns comparison. In that way, this method matches an equality operator or anything of higher precedence. So moving on to the next rule. This is
Why is it that
the same thing? Yeah.
why is it that equals has to be equal and not equal have to be considered before the less thans and greater thans? Why isn't it all six of them at the same precedence level?
That's just how C does it. Like he's following the same rules as C. So I guess,
Why does C do it that way? Or am I just not thinking?
Historical reasons. You need to do it in some way.
yeah. So I guess, what were we talking about? Like, 5 greater than 3 equals 2 less than 7. So these will get evaluated to like bools.
Oh yeah,
So
I guess that
what,
makes sense then.
and then you want to compare those bools. So I guess what would it even mean to be the other way?
Right, then you would be comparing 5 to the Boolean of 3 equals 2, and that's silly.
Yeah. So if it was this is the other precedence.
Right.
Then then it's a less than or equal to, let's take a comparison of bool against bool. Yeah.
Okay, thank you.
So yeah, so this next one, about the same. It's just a different set of operators, but it follows the same structure because it's another binary operation with the same associativity. And then he says that. And then term. So term, now he's matching the different set and does the same thing. Multiplication and division, matching a different set of operators and does the same thing. So I get, oh wait, where do these, oh yeah, that each one's like higher precedence than the previous. So term goes into here, factor goes into here, unary goes into here. And then unary might be a little different. So yeah, that's all the binary operators parsed with the correct precedence and associativity. We're crawling up the precedence hierarchy, and now we've reached the unary operators. Code for this is a little different. So here, because you can't have any number of groups, you just have one if instead of a while. And then you call yourself recursively because you're allowed to do that for unary. Although interestingly, he has an early return. So if this matched, then we know we're in this production rule. So we have to return a new unary with that operator. And then otherwise we go down to primary. All right. And then primary, this is the last one. And then I will end it because it's about 8. So primary, otherwise we must have reached the highest level of precedence, primary expressions. So most of the cases for the rule are single terminals. So parsing is straightforward. So if you exact match any of the terminals, then you just make a literal. And then you need to have some way of extracting the literal out of the value you just read. So for false and true, you just make it literally the Java of false and true, and then null. And then if it's a number or a string, you need to figure out the literal value from what you just looked at. That would be like in the, we made that one in the Lexer. Otherwise, you are in a parenthesized expression. So you go all the way back up to expression, the highest level or the lowest level, and you return that. And interestingly, what happens if none of those were the case?
Right.
It just can't happen, I guess. I don't know why Java lets you do that.
I mean, I guess they're assuming that in the grammar that can't possibly happen, and so it's safe to just return without returning anything.
Yeah, what does it actually mean? If we don't, that's an error.
No, that's for the right parenthesis on the end of a.
Okay, sure. Yeah. Oh, gotcha. Yeah.
But
Okay.
then
I don't
shouldn't there
quite
be something
understand
at the end there?
I don't quite understand why there's nothing at the end. That's weird. Okay, cool. Well, that's the parsing by recursive descent. That's weirdly easy. We went over all these like bottom up techniques in compilers class, and it was really complicated. So I'm glad that you can just do it this way and it's not a problem. All right, cool. We'll go ahead and stop recording.